So we're looking at permutation statistics in a little more depth, and we're going to be looking at one in particular that comes up in many different guises, which is called the major index. When it was originally introduced by Percy McMahon in around 1915, he called it the greater index, and we'll see where that greater term comes from. It's called the major index because McMahon was a major in the British military, so it's called major index in his honor. So it's defined on permutations. We call it MAJ for major, and it's the sum over all places where you have a big number followed by a smaller number, and we sum up the position. Sort of looks like a bizarre thing to do, so let's do an example. So I'll take a nice big permutation of 9. Let's take a permutation of 9. There we go. 7, 2, 5. Okay, and let's try to compute its major index. Maybe we'll switch colors to make it stand out. So if I want to compute the major index of this, I look for any position where I have a big number followed by a smaller number. So here, the 8 is bigger than the 3. The 8 is in the second position, so I add 2 to the major index. The 3 is smaller than 9, but 9 is bigger than 4. It's in position. The 9 is in position 4. The 4 is bigger than the 1, and the 4 is in position 5. Not the 1, but the 7 is bigger than the 2, and it's in position 7. And so the major index for this particular example is 18. Okay, and we can compute that the major index is always going to be a number. So the minimum, these are sort of nice values to compute. What's the smallest major index that we could have? Well, it's 0. And this happens at the identity, right? 1, 2, 3, up to n. There are no descents. There's never a place where you have a big number followed by a small number. So you're going to get major index of 0. That's, of course, the smallest you can get. Well, what's the biggest that you could get? That's another thing that we can consider. What's the maximum MAJ? Well, the maximum MAJ would be if we had a descent everywhere possible, right? So that's going to happen when we have the permutation n minus 1, all the way down to 1. And now we're adding up the numbers 1 up to n plus 1. So this is the sum from I equals 1 to n minus 1 of I, which of course is n choose 2. So those are sort of our extreme cases. Let's do a little more exploring of this idea, and let's maybe do a table for something small like S3. So if we're going to write down all permutations of 3, we can write them in lexicographic order. It's a really good idea, unless you have some reason to generate permutations in a different order, to start with lex order. And now let's compute the major index for each of these. So, of course, we have the identity, which is 0. Here is a descent. It's in position 2. Here's a descent. It's in position 1. A descent in position 2. A descent in position 1. And now we have 2 descents in positions 1 and 2. And so we get a MAJ of 3. So we can play that game, okay, get some kind of intuition for MAJ. And what we want to think about now is think about the major index generating function. So for now, I'll call this m sub n of q. Just to define it, it's just going to be, q is going to keep track of what our major index is. So this is the sum over all permutations in Sn of q to the major index of w. This is going to be a q analog of the size of the symmetric group. So a q analog of n factorial. And we can compute it for this example that we did. So let's look at our example. We did m3 of q. And we can just write down this is going to be q to the 0. This is going to be q squared. This is a q. This is a q squared. This is a q. And this is a q cubed. So just consolidating our terms, we get 1 plus 2q plus 2q squared plus q cubed, which you might recognize. And if you didn't, one thing you should do when you have these sorts of things is factor them, because it can lead to interesting things. So we factor this and we realize, oh, actually we've totally seen this before. And that leads us to McMahon's theorem. So his theorem says the following. It's going to give us a formula for the major index, for this major index generating function. And it's why we don't really use this notation for it, because there already exists a perfectly good notation for it. This is the standard q analog of n factorial, which again, I'll remind you, this is 1 plus q. That's the q analog of 2, 1 plus q squared times 1 plus q plus all the way up to q to the n minus 1 is the analog of n. So next time we're going to prove this theorem, and we're going to give a combinatorial proof of it. This is the same thing that we got. This result is the same generating function that we got for inversion numbers. That's another thing that you can think about, is that the distribution of the major index is the same as that for inversion numbers. So we'll deal with that in the third video. But for now, take a moment between the videos and think about why this expression might be true. We proved it for the inversion number. We did it just by getting a recurrence. Can you do the same thing for the major index? See what you can come up with.